Hello. Wait, I don't, why do I miss? Hello, hello, hello. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Hello. Okay, hello. Lear, hello. Vicky, hello, Sonam.
Hey,
Hello.
good morning.
Morning. Good morning. Hello, Aminata. Hello, Anthony. Hello, Bridget. Hello, David. Okay. Okay. Good afternoon for the double Vicky. Good afternoon, Raina. Hi, Melanie. Hello, Anthony. Good
Good
afternoon.
afternoon.
Good after. All right, Zoe. Good afternoon. Thank you. Hello, Anthony. I said, good afternoon, Victoria. Good afternoon, Bridget. Good afternoon, Caitlin. Good afternoon, Aminata for the double. Good afternoon, Sonam for the double. Good afternoon, David. Okay, who did I miss? Okay. Oh, and I think that's good. Yes. Okay. Okay. Um, and good afternoon, Gabriel. Yes. Okay. Right. And Mafine and Bridget. Okay. Oh, I love that. Wow. Okay. It's like I'm like teaching in the Bronx Zoo here. Okay. And good afternoon, Joel. Okay, I want to get wait more. Okay, very quickly. Wait. Um, good afternoon. Good afternoon. Okay. What just happened? Hold on. Okay. Um, as I think I indicated, for good or for bad, what I like to do in the last class, in the last classes, but particularly the last class, is I like to do physics. As soon as we get rolling, which is momentarily, I want to give you the last bit of material that act in my mind puts all this together and sort of makes all of this physics work for 2 semesters worth it. I mean, for me, physics is a story. You've been going through the chapters of that story since day one, since Galileo's principle of relativity at the beginning of physics 203. I mean, if you took it here. And to my mind, this story leads somewhere. The story, I mean, the story never ends, of course, but there are certain big beats in the story and certain climactic moments in the story of physics. And I like to get to one of them by the end of physics 204, i.e., today. Um, so once I lit, so the good news and the bad news is we're going to do physics today. I'm going to explain something from physics to you. Like I mentioned, uh, yesterday, Monday. Well, I'll get to that in a minute. I mean, the bad news is you still have to do some physics with me. The good news is I think it's exciting physics. Um, and I will tell you right now again the way to follow what I'm saying today, because I will speak somewhat quickly and it will be conceptually thick, perhaps. Um, the I want you to have these final concepts. You don't have to get too worried about how to solve problems with the concepts, but I want you to see the concepts, and the concepts themselves are indeed mathematical. The way to follow along today, the way to follow along today, once I get rolling, is to have um, that true false document out in front of you. The true false document that's in at least one, if not both, of the practice uh, final exams from past semesters. The final exam from either last semester or last year or both has like a Google Forms in it, a true false section. If you if you have that out in front of you while I'm talking today, it will help you listen. You'll see the kinds of questions that I ever ask about this. You'll see how it is I'm trying to hold you responsible for this material. Hopefully that will allow you to kind of relax a little bit, even as I will not sound relaxed. I want you to try to get the big picture of physics that I'm trying to get across today. And again, so have that true false document in front of you. If and when I remember, I'll try to point you to, oh, this is one of the true false questions right here. If I can, I will. I won't definitely. I'll also ask you that once I start rolling, with the physics, in a kind of an unusual way to end the semester, I won't be asking for your participation. I just want to get to the end of this story for you, with you. So please forgive me in advance that even if it goes a little fast or something like that, I'll just ask you to rewatch the video later or watch old videos of the same thing. Um, because this is my last opportunity to land the plane for you. So it will be hard for me to answer questions or get off. This is not a day for me to sort of take side roads. Um, so that said, so again, momentarily, once I start the physics, it's just going to be physics until 1:30. Um, so so I'm going to take a minute or two for us to make sure that logistics and everything are clear. I'm going to tell, wait, are we record? We are recording. You are there. Okay. Chat, I'm going to remind you again that if there's any issues at all with your expectation of the final exam or your grades or your life or anything, I'm reminding you again, please reach out to me by email or send me a text to this number that I just put in the chat. And if we need to make a phone appointment or something like that, we will. This is another way. So I'm still available. And I will be in my office next Tuesday, by the way. That's maybe too late for many of you. I mean, Tuesday night is when the final exam is due, but whatever, I will be around, whatever. But if you have future plans or recommendations or graduate school or being a lab tech or something, I'd love to talk about all of that with any of you. I hope you are not strangers after this. It has been a great privilege and pleasure to be with you. And I'm not kidding. It really is a privilege and a pleasure to be with you. Um, I hope we all got something out of this. I did. Also a reminder, please, if your head starts, please, a reminder to do the course evaluations. Please remember you get 20 points if you do both of them. If you just submit a screenshot that you did them, of course I won't see them. I promise. I can't if I mean I won't know who wrote what. I promise I can't if I wanted to and I don't want to. But if you do them, you get 20 points. Um, um, other reminder, again, I think it's clear. I hope it's clear at this point. The final exam will be posted no later than 8 p.m. Friday. I'm going to try earlier, but I can't promise. Be posted no later than 8 p.m. Friday. Be due back midnight Tuesday. Again, so that you're clear. I think I made this clear Monday, but it's possible that one of the problems on the final is that you redo the worst of your problems on the midterm. If that is a thing on the final, if I ask you to redo a problem from your midterm, then it has to be the one that you did the weakest on, and you must redo the whole thing. You can't just submit corrections. So even if you did really well, then bask in your own glory and redo all the good stuff that you already did once and improve it with the corrections. In other words, it's supposed to be a better draft than whatever you did in your midterm. It's supposed to include what you did in your midterm, but better. If so, that's possibly on the final, but maybe not. Also, possibly on the final, is any other combination of the problems from the two documents made available in Google Classroom. Any combination of those, maybe choices, maybe not. I don't know. Um, Again, the promise though that if there are circuits on the final, you'll have the opportunity to choose out of circuits. You won't be forced to do circuits because I never talked about them. Okay, so I think those are the logistics. I believe those are like, and again, your grades will be submitted to CUNY first by the night of Tuesday, the 27th, a week after you submit your final to me. You'll get a grading spreadsheet like the day before with the full transparent breakdown of how your grade was calculated and all that. So you have an opportunity to see it before it's posted. Other than that, I will just be rushing to do all the grades during that week. So please forgive in advance. Okay. That's a good question. Uh, uh, um, I've someone's asking why did I not talk about I in recent semesters I have stopped talking about circuits in the lecture because it seems like in recent semesters such a thorough job is done in the lab with circuits. Has seemed redundant for me to do it also, and the truth of the matter is that what I'm really interested in for me and for you is the fields, which are much harder to talk about and deal with in the lab, and are a little bit more my and I'm in recent, to be really honest, in recent semesters, somehow wasn't able to get to magnetism, which is very important to me and I think very important to this course. And today is where I'm going to tie magnetism back to everything else you've done and show you why magnetism takes such a big role. So even though we've only been talking about it for a couple of classes, we have. And so to the really honest answer to your question, and then I'm going to go on, is somehow because things are harder to do efficiently on Zoom, we time has started to become more of an issue. And I started finding in recent semesters that by spending time on circuits, I couldn't get to magnetism. And so I feel that circuits can be more adequately done in the lab. And so I'm doing the magnetism. That's basically the reason. But for good or for bad. Maybe that's not a good reason. But for that reason, I'm not going to force you to answer questions about the circuits in the final since I didn't actually address them. But you still might have a choice, but you won't be forced. Okay, so that's. I mean, I love circuits. So if you want direct chat person, if you ever want to meet me in my office or make a Zoom, I'd love to talk about circuits with you if for what it's worth. But but fair question. Okay, any other? So again, in a minute, I'm going to sort of go bananas with physics material that I want you to know the concepts. I want you to follow as best as you can. The way to have the true false in front of you if that helps you as a guy, but take notes for sure, take notes. Um, well, that's an interesting okay. Um, It says, Professor, will we be able to rebuttal our grade kind of? I mean, that's an interesting word to use. What I'm saying is you will see your full grade breakdown before it goes into CUNY first on purpose for that reason. Yes, if next Monday or Tuesday, when you see your full grade breakdown, if you have a question or concern, if you either think I made a mistake or I overlooked something or something, yes, there's an opportunity for you to reach out to me before it goes in. So the answer is yes. Now I will say, I mean, the idea that you're calling it a rebuttal or that you know, if you're already thinking there's going to be an argument, that's interesting to me, and maybe you should reach out before. Like, if you already think there's an issue, yeah, definitely text me or email me and let's talk about it. And I don't mean that sarcastically. I mean, I don't remember what I'm talking. Obviously, this is a direct chat thing. I don't remember what the person got in the midterm, so I don't know. If you're talking about like on your midterm grade, you certainly should reach out to me. If you don't understand why I took off points somewhere or you can't read my handwriting, certainly reach out to me. Um, if you're concerned about your overall grade, I do think it's probably it may work out better than you think. I mean, don't get ready for a fight yet. But yes, you'll have an opportunity to question your grade before I submit to CUNY first. Everybody, you do. And I do make mistakes. And I'm open to be clear, and I hope I'm not sounding, I don't mean to sound combative. I recognize that I can make mistakes or that there's a lot of things you're learning about your grade at the last minute, which is very jostling. So absolutely you have an opportunity to influence the final judgment if you feel that something was off. Like, yes, I'm open to that. And I'm not defensive about it as long as you, any of you, if you come to me with a question, if you come to me like with respect and peace, like, I think there might be a question here. I'm confused about this. Could you look into this? I will absolutely do it. I'd rather your grade be higher than lower, and I'd rather it be fair, not unfair. And I'd rather we both be on the same page for sure before the grade goes in. So yes, but just my advice to everybody, and I hope that okay, no problem. No, I'm being a little defensive. No, sure, and I get it, and it's a very legitimate question, and that is why I'm trying to get this like clear now before I like dive into the physics. Is yes, I recognize I've been doing this for you. I recognize how important your grade is to you, and I recognize I have to do a million of them, but you only get one. I recognize that. So things happen, and you should, and I recognize that it's jostling not to be able to track it as you go. As you know, in some classes, it's easier to do that. So absolutely. you'll get a moment before it goes to CUNY first where you'll be able to see it in its full glory and question it. So the answer is yes. And yes, as a person's already made clear, yes, the more, and I've definitely changed grades in the past. I'm not one of those people that says, no, if I did it, it can't be. I will be very open to the possibility that there something might have gone wrong or said blah, 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 blah. And I'm rooting for you to get it. I know I'm overstating the case, but I do think that's a very legitimate concern. I want you to do well. It's in my interest as well. So if you anyway, so yes, you'll have an opportunity to question. Just my request to all of you is if you see something you think is wrong with your grade before it goes to your first, do reach out, but reach out respectfully, like compassionately. I will have compassion for you, but please understand that I too am doing my best under time pressure. So I'm not looking for a fight, and neither are you, and we'll work it out. Is okay. Um, okay, no, that's totally yes. Oh, okay, okay. No, good to know. I hear you, direct chat person. No, and it is very important. And okay. Um, okay. Wait, so that's okay. Hold 1 second. 1 second. Okay. Okay, so no, yeah. So all of this, I'm about to I'm just looking 12:32. Okay. All of this, look, I'm going to miss you people, and I hope you're not strangers, and I hope you do reach out for help with your future, or that I become helpful in your future in some way, or maybe you lab tech or something like that. I'm serious about all that. The reason I'm saying that again, and it's all weird that I've only known some of you electronically. I get that. But I mean, what I'm trying to say is that there's two things, right? There's academic success and there's intellectual joy. I'm in it for both. Okay, like you can't like I'm in it for both, and they're not let always the same thing. So right now, in we're making sure that we're okay in terms of academic success, that we're all rooting for you. And again, I'm saying one last time, phone number there. If an issue comes up in the next 2 weeks about your academic success, I'm here. That doesn't mean I can promise it to everybody. Like, obviously, we're in it together. You have to do your part. But I can promise that I want it for everybody. And I'm not an obstacle to your success. I'm supposed to be an advocate for your success. Like I am, okay, but it's anyway, you get all that. So I'm saying all that to say it's important. It's really important and it's over here. Now, if we're okay with that for the moment, if you understand that if any academic anxiety or anything comes up in the next hour, you're going to park it and you're going to reach out to me later with my cell phone or with my email and we'll confront it, okay? But that being said, I'm now going to shift gears for the next hour and I'm going to like dump physics on you and please join with me in taking it. And it's going to end with physics. Because I'm going to be right up against the clock when I do. If I'm talking fast or frenetically, it is because I care about this so much. I want it in your mind before you leave, before I don't get a chance to teach you again. I'm serious. So forgive me that it's 12:35. I'm about to like switch the view on the screen and switch gears. And this is like if there's no more, if we're good to go, this last physics is physics I want you to know. I need you to know. I want you to carry with it. And I just want it. And all you're being asked, the only responsibility you have toward it is to be able to answer true, false questions if you choose that on the exam, if it's on the exam. And other than that, don't try to fully grasp like every detail of everything I'm about to say, but try to get the big picture enough. My biggest hope is that you'll find what I'm about to say interesting enough that you'll ever want to think about it again or read a book about it or see a movie about it or a website about it. Like it's not meant, it's meant to be motivational. It's not meant to be demotivational. Okay, so I'm going to switch the view on the screen. Uh, okay, can I have a thumbs up? Can I go? So can I do physics for an hour? Are we? Or that's a th or that's a thumbs or that's one thumbs up. Can I do? I'm going to start talking physics now. Am I good to go? Are we good to go? Oh, yeah, yeah. Wait, there's only one thumbs up. That's scary. Okay, two. Wait, it's still only one. I heard it. Well, I'm gonna go. I'm gonna go for it. All right. Okay, so here comes the board. I do want you to do please take notes like next year. Remember we have these just take a note of these two constants, the ones that keep coming up in all the fundamental equations. They're just constants of proportionality that make the units work out, but they keep coming up in each of our equations. The epsilon naught comes up in all the electricity equations, and the mu naught comes up in all the magnetism equations. They're just constants. I'm not asking you to memorize them, but I do want you to have them on a piece of paper. Now, in fact, I should even say before I go any further, what would be really convenient is any of you who happens to have a calculator in front of you. I'm going to say something at a certain point about these numbers, and you may want to even check what I say. So if you have a calculator in front of you ready to go, that would be very helpful too. It's not a requirement, but it'd be very helpful. Now, the other equation is what I'm trying to get to. So here we go. Here's what we have so far in terms of electric fields and magnetic fields. Over the last few weeks, we've established this. And again, please, even if you've seen this before, it can't hurt to write these a million times. These are the equations we have so far. I mean, we have a lot of other equations in the class and all that, and in life, but just up to about 1879, the year 1879, there were a bunch of equations, in labs all over the world, and were all written in different ways, in different forms of math and stuff like that. But these four existed by 1879. These are Gauss, and again, please take notes. These are Gauss's law for magnetism, Ampere's law, and Faraday's law. And if you look at I'm picking out these four equations in particular, like in the last three, we only got in the last class. I'm aware of that. Okay. But what if you look at the left side of these equations, there's a certain pattern or similarity among the left of all the equations of the left side. There's a reason to sort of focus our attention on these four. These four kind of together describe the shape or the character of electrostatic fields and magnetostatic fields, electric and magnetic fields in the world. There's two equations that describe the shape or the character of electric fields, and there's two equations that describe the shape or the character of magnetic fields. Like remember, E stands for electric, B stands for magnetic. And also notice that there happen to be two equations that are about closed surface integrals or closed surfaces, and there's two equations that are about closed paths. So there's a certain tidiness or, rhythm to the left sides of these equations, the way we're looking at things. And remember, we said, And remember, and notice, like we said yesterday, there's a certain relationship between dimensionality in each one of the equations. Like, and again, I'm very aware, believe me, that a lot of this stuff is like brand new to you. Like three of these equations I only introduced 2 days ago. I get that, but I'm trying to give you but I'm trying to give you the big picture and the rhythm. Like if you want really, well, slight sidebar. One reason we've been on Gauss's law for so long and why there is a big chunk in the final exam about Gauss's law is if you can get, and why there's a whole homework about Gauss's law, if you can get your mind around Gauss's law, all these other equations have the same character. They're sort of all built from Gauss's law. Gauss's law is the center piece of all of this. And 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 what happens is, and so the second equation is just the magnetic form of Gauss's law. They're both about what's going on through closed surfaces. How many field lines can we find coming out of a closed surface? Then the next two laws, which are the newer ones to you, the next two laws take that same character, but they shift it down a dimension. The thing I want to remind you, I'm going to remind you right now, we've said it before, we're going to say it again right now, is what we're saying is this. Notice the character of all of these laws is very geometric. The assumption that we're making, I'm just going to repeat, this whole thing is really about regions of space and the boundaries surrounding those regions. The assumption is that a region of space can be either bounded or unbounded. Bounded means limited, like a boundary is an edge where the region stops and a new region begins. A region can have a boundary or not. And also at the same time, a region can be open or closed, not the same thing, right? And this applies to any kind of region. So the assumption we're making or the belief that we have is that, well, that if you take that a piece of paper is an area, right? A surface, a two-dimensional region. A piece of paper can be open like this, like if my hand were a piece of paper, it's open. Why is it open? Because it's not closed. If I close it, that means I take all of its edges and touch them together and I wrap it around and I'll know it's closed because a mosquito or something could get on the piece of paper. If it's closed, a mosquito could start walking in a certain direction and never turn around, never make a turn, never change direction, and eventually end up where it started. That is what closed means, right? So a surface could be open or it could be closed. When it's closed, when the surface is closed, it becomes the boundary to a recognizable volume within, a unique volume, unambiguous volume within, right? So a closed surface is the boundary to a unique volume. A closed path, similarly, a path, a one-dimensional region of space is open if it's just like a line segment or something like that. But if I bend it in on itself and take the edges and touch them to each other, then a mosquito anywhere in that circle could walk forever and eventually, I mean, could walk in a straight, could walk without turning around or changing direction and end up where it started, right? So that ring, that path would then be closed. Now it's understand when you close a path, it's still a path. It's still one dimensional. Its length is still a length measured in meters. Just like when you close a surface, it's still a surface. It's still a region of space that only has two dimensions and is measured in square meters. But you see the parallel between the two statements. I'm saying a closed path is the boundary for the open area that is enclosed within, right? Like it's just like a closed surface is the boundary for the volume within. A closed path is the boundary for the area that lies within. Okay, you see the parallel. Just notice one interesting, like different word that's being used there. When we say that a closed surface bounds a volume, we can say unique volume. We could say an unambiguous volume, or we do say an unambiguous volume because we don't know if the volume is open or closed. Like I don't have very quickly when you close up. Notice if I close up a path, even though it's still a path, I need a second dimension into which to close that path. You can't close a one-dimensional region of space without having a plane within which to work, right? So I can close paths and I can close surfaces. But when I close a surface, I go into uh, um yeah, I guess really quickly, but then okay. I mean, I'm saying like here is a closed path. Sorry. That's a good question. I may have to not honor questions today. Sorry. That is a good question. Someone's asking, can I draw it? And I will be drawing these things in a minute, but I think I'm trying to say, so if this is a closed path, it is the boundary to the area within, is what I'm saying, right? The area within that boundary, the area, the circle, with the disk within the circle is an area. Now, it's an open area. It's bounded by the circle, but it's open in the sense that I didn't wrap it around itself. That's what I'm saying. I hope that helps a little bit. What I'm saying to everybody is that notice whenever you close up a region, you have to go into the higher dimension of space. If you close a path, you need two dimensions to close it in. If you close a surface, you've got to bend the piece of paper into the third dimension. Well, so a volume then, I don't know if a volume is open or closed because I would need a fourth dimension to bend the volume into to close it up on it. I'm not from the drawing, an open area. Okay. An open area would be a surface, right? Not a field, a surface. Like everything I'm saying right now, that's a good question. Everything I'm saying right now is about just space in general. This isn't even literally about the fields yet. I'll go back to the fields in a second. But right, like the open area bound within is the area of space, literally. I mean, that's a good, I hope that clarifies. Um, so okay, so back to fields. So what I'm saying here is a closed path bounds an open surface. It's open because it's not closed. It's open because it's flat. I don't mean it's unbounded. I don't mean it's going on forever. I mean it's open because it's flat. It's not closed. I, I, so a closed path bounds an open surface. A closed surface, well, I can't say it bounds an open volume. I don't know the difference between open. What I definitely cannot draw for anybody is an open volume versus a closed volume. That I can't conceive at all. I would need a fourth dimension. I'm not saying they don't exist. I'm just saying we can't access them or conceive of them because we would need a fourth dimension of space to do that, right? But so this yellow thing is an open area in the sense that it's flat. Like, whereas a closed area would be the skin of an orange is a closed area, a closed surface. A container is a closed surface. So what I'm saying about fields now, I'm saying these four equations that we have, they maybe look all crazy, but especially the last two, the new ones, right? But if you look at the last two equations, okay, here I'll draw. I'm going to draw the third equation. I'm going to draw what the third equation is trying to say. The third Ampere's law. Okay, this diagram. Okay, thank you, direct chapter. Okay. Hopefully this drawing a little bit makes sense or helps. It's partly because someone just asked for a drawing, but it's also, I mean, this is what I want to say. Like, look at that third law, Ampere's law, which is new. It's trying to say if you take a closed path, like a circle, you walk around a circle in space, a circle, I mean, literally the circumference of the circle, that is a closed path. You can make a round trip around it. It's one dimensional. It's like 2 pi r or whatever. If you walk around that circle, adding up the B field as you go, adding up the total amount of B field around that circle, what Ampere's law is saying is so the total amount of B field, a magnetic field around that circle will be fully determined by a constant times the current enclosed. What does current enclosed mean? It means all the current that passes perpendicularly, fluxes, passes perpendicularly through the area enclosed by that path, or in other words, the area bounded by that path. The open area, the yellow disk is an open area bound. What might be confusing some people is the word open. Open does not mean unbounded. It doesn't mean infinity. It means that it's not closed. It means it's not a surface area. It's not a package. It's just a flat area. So what we're saying here is if you have a circle, the interior, if you have a circumference, the interior of it is like a disk, right? Any amount of current that goes perpendicularly through that disk is what determines the full magnetic field around the circumference of the disk, right? It's like saying, and I'm going to go on in a sec. Oh, I really am going to go on in a second. It's like saying, um, it's like saying that if you have a container in space, Gauss's law, you have a container, the total number of E field lines coming out of the container are fully determined by the number of charge points enclosed within the volume of that container. We're saying all electric field lines have to be accounted for by charge. Well, here we're saying all magnetic field lines have to be accounted for by current. And they're accounted for in the same way, only one dimension down. Magnetic field lines are closed paths. So if you walk around a closed path, the full magnetic field that you'll find is fully determined by the current passing through the area bound by that path. Okay, that's what Ampere's law says. So it's okay. And then Faraday's law, the other one that we did yesterday, quickly, Faraday's law is very similar again. It's a little bit more exotic. Faraday's law for electromagnetic induction, the last one, okay, says, okay, you know what else? It turns out, it turns out that if you have an open area, a flat area, like a square or a rectangle or a disc, whatever, and you change the magnetic flux through that area in time, right? This is what you learned about in sixth grade or something, like electromagnetic induction generators. How do they work? They work like this. It turns out if there's an area through which the magnetic flux is changing in time, DDT, literally precisely the amount by which the magnetic flux changes in time through an open area will induce electric field, electricity, in the closed path bounding that area, right? So, now why? Well, first and foremost, Faraday predicted something like this would work if he moved a rod, on metal rails through a magnetic field, because he knew that charges moving through a magnetic field would experience a magnetic force and cause a current to flow. So at first it made sense from the other laws, but then it turned out that it's true under all conditions, even when you don't move a rod and you just strengthen the magnetic field. It turns out to be its own law that if you do anything to change the magnetic flux through an open area, that will induce electricity in the perimeter of that area, in the closed path bounding that area. So what I'm trying to say in big picture terms is that every single one of these laws says something about magnetic fields or electric fields, or in the last case, both. Every single one of them is asking us to look at fields through space by looking at the region of space and the boundary of that region. Every single one of these is saying something like, if you want to see what the field is doing through the boundary of a region, look inside the region for what's causing the field. And in two cases, it's the region is three-dimensional and the boundary is two-dimensional. In two cases, the region is two-dimensional and the boundary is one-dimensional. Okay, so that's the state of affairs as of eight. Oh, wow. Good. Great question in direct chat. I'm not going to get 100%. The third Ampere's law is 100% related to Stokes' theorem. I'd love to talk to you about that more privately, one-on-one. Great connection you just made. That's a whole discussion, but 100%. And Gauss's law is the divergence theorem or Green's theorem, like very related, very related. In fact, everything I'm about to say comes from the fact that Maxwell understood that relation and applied it here. I can't get into that now, but great question. Yes. In effect, the two path integral equations here are really curl equations, and the two, I don't want, anyway, great question. Great question. Yes. Um, all right. So there's this mathematician, physicist, Scottish mathematician, physicist named Maxwell in 1879 looks at these equations and notices the pattern on the left-hand side and is doing a lot of advanced mathematics on his own. He's developing vector calculus, multivariable calculus, and is so analyzing these equations in a higher mathematical level kind of way. And he starts staring at Ampere's law, this one that I just drew. And he's staring at it and he's into it, but he realizes something is incomplete about Ampere's law. He realizes All right. Basically, he realizes that what I just drew, well, it's what it says here is Ampere's law, according to Maxwell, James Clerk Maxwell, Scottish physicist, mathematician, in 1879, he realizes Ampere's law is right. It makes total sense. It's just like Gauss's law, but it actually makes total sense and complete sense only if we're assuming a current that is steady in time, that doesn't change in time. Maxwell says, wait a second, consider this. He says, oh, wait, okay. Right. Oh, totally. Oh my God. So someone else, no, yes, I can't get into this right now, but someone else is also making a connection to their multivariable calculus work. This is a second person. You're totally right on the money. And honestly, we used to, I love all that stuff. Like div grad curl and all that makes this stuff come alive even more. I would love to talk to you privately at some point about the connections between this and that. And all that stuff comes from Maxwell. So you're absolutely making the right connection. I'm super excited. But oh, you definitely could say that the line integral represents the work done by the electric. So yes, like your answer is yes, yes, yes. I just can't. In a way, everything I'm saying now is 100% about that. I'm just doing it in a different language right now for the sake of this course. But yes, that's awesome. Please come by or shoot me an email at some point about that. But okay, what I'm saying here is imagine you have a circuit that has a device in it called a capacitor. It's just two plates, metal plates that initially have no extra charge on them at all, but are meant to catch charge and store it. Like it's called a capacitor, and you put it in a circuit on purpose so that the charges, when they're flowing around, they get stuck on the plates and they build up on the plates, and this thing stores up charge. And slows down the current in time on purpose so that you can create a current that actually varies as a function of time. So what happens is once the current is flowing in a situation like in a capacitor circuit, charge begins to build up on the front plate and it gets stuck there, but the voltage in the battery is continuing to pull everything around. So positive charges leave the other plate. So negative charges build up on the other plate. Um, and this creates a reverse voltage and starts slowing down the current and this is all on purpose. This is all standard and known. And it creates a current that exponentially decreases as a function of time. So it's a non-steady current. Maxwell says, look, if you try to apply Ampere's law to a situation like this, a non-steady current, you'll notice something interesting. If you draw that closed path, if you draw a closed path, say over here, and you think about the B field around that closed path, for sure there will be B field. Like if you took a meter above the current, you'd measure, you would measure magnetic field. And for sure the information is there. The circuit continues to work because the circuit's working. Even though charge lands on the first plate and does not go across to the second plate, charge gets stuck on the first place, but somehow the whole circuit continues to work anyway. And we can recognize that because we can see magnetic field above the circuit at the top of some circle that we could draw around the line. And Ampere would say, oh, the current going, sure, there's magnetic field up there because there's current going through the area bound by that loop, that closed path. But Maxwell says, but if I take your law really seriously, if I take your law really seriously in this case, remember we said, like over and over again now, we said a closed surface bounds a unique volume. We said a closed path bounds an open surface. Remember, with open, like not closed, and that's true. We can say that a closed path bounds an open volume. We could say it's open because we can tell the difference between open and closed in 2D. What we didn't say was unique. We didn't say it was one and only one surface. We said it was an open surface. In other words, Maxwell says, if I take your law really seriously and I want to look at the current enclosed, couldn't I imagine that the area bound by your loop, couldn't I imagine that the area is made of like plastic or like rubber? It's like a balloon, right? It's like a flat balloon now that hasn't been blown up. Couldn't I blow up the balloon? Couldn't I, or if you consider this to be like rubber or plastic, couldn't I punch it out, not break it, but just expand it out so that the area stretches behind? And this, now that's hard to picture and hard. I'm going to try to draw it, but I'm not going to draw it well. He's saying, look, imagine that the area you're looking at is punched out like this, so that it's a balloon that we blow up and contain one plate of the capacitor, but not the other plate. Now that's a bad drawing, but that's what I'm trying to say. So imagine you blow up a balloon and you put one plate of the capacitor in it and the other plate behind the balloon. So that balloon, the whole area, the skin of that balloon, that's still an area, right? It's not a volume. The volume is the air within the balloon. But the balloon material itself, that's all a big area. It used to be flat and then you blew it up. So now it's a bigger area, but it's still an area, and it is still the area bound by the neck of the balloon, right? The neck of the balloon is still the border line, the boundary. If you're a mosquito walking around on the balloon, you can walk anywhere on the balloon, but once you hit that neck and you cross the neck, you fall off the balloon, right? So that whole area is an area bound by the closed path. And this sounds like a very obscure argument, and it is in a way. It's a way of really taking seriously, is this really a law? Does this really work in all cases? And Maxwell says, in this case, if I consider the not flat area in a not steady circuit, what I would see is current does not flow through a ballooned area, a stretched area. Yet there still is magnetic field. So what I'm trying to say mathematically is that Maxwell is saying, if you really believe, just like with Gauss's law, we were trying to say any closed surface at all, count the number of field lines coming out of the closed surface, it's fully determined by the charge within. Any closed area at all. Here, supposedly we're saying any closed path, any area bound by that path, the magnetic field around the closed path should be fully determined by the current going through the area bound by that path. And Maxwell says, well, not if the current isn't steady, and not if you cleverly pick an unflat area. We never said areas had to be flat, says Maxwell. We said they had to be open, like they had to be bound by that loop. But no one said they had to be flat. You're saying any area, any loop. I say no, not if the current isn't steady, and not if you pick this funky area, the area of like a balloon rather than just an uninflated balloon. Very picky, but we are talking about laws here. So, and Maxwell's not doing it to be a jerk. And the truth is, for those of you who just brought up multivariable calculus, the real reason Maxwell came up with something so obscure like this totally was not to be a jerk. It's because he took the divergence of both sides of Ampere's equation, which can be written as a curl equation, and the divergence of the curl is always supposed to be zero. So he knew something was wrong on the right. I mean, that's for a couple of people in the class, but he knew something was incomplete about the right side because of mathematics that he was developing sort of on his own. So you guys are right to be bringing up divergence and curl and all of that. But he because he had a math reason for thinking about it, he then really came up with a physical, experimental, big exception to Ampere's rule and said, your law doesn't hold up in all cases, but I want to help you, Ampere. Maxwell says, I want to help you. I'm not throwing out your law. It's obviously really useful. It obviously holds up under steady cases. Let me add a term to it. Let me help you out and make it more complete. He says, look, there's obviously is magnetic field wherever there's magnetic field. I mean, if you put a meter there, the field is going to measure there regardless of what circles you're drawing in your mind. I mean, he's not trying to be ridiculous. The magnetic field is there or it isn't. It's not going to change just because we're drawing funny circles in our mind. And more to the point, what does that really mean? It means it is there because this circuit works. Like circuits, the charge continues to go around and around, even though there's a gap between the two plates. Even though no charges go from one plate to the other, somehow everything still functions and the current still does what it's supposed to do. Why? Because Maxwell says, look, even though no charge is going through that open area, even though no charge is going from one plate to the other through the open area, something is going through the open area. Somehow this circuit is working. What's going through the open area? The electric flux due to those charges that got trapped on the first plate. Like Maxwell says, remember Gauss's law. For every charge, there is an electric field line. That's the point of Gauss's law. So even though those charges are not making it through that area, their electric field lines are fluxing through that area and making it to the other side. And that's what's continuing the circuit. Maxwell's saying, the way space ever knows that there's charges about is that space feels the electric field from those charges. You don't need to send charges across to make the circuit work. It's sufficient to send electric field across, which is what's happening here. And that's why the space up here knows it in the form of a magnetic field. In other words, Maxwell says, Maxwell corrects Ampere's law, makes it more complete, and says every bit of magnetic field in every closed loop in the world, can be in totality accounted for by up to two possible contributions. Regular everyday standard current can make magnetic field, sure, we already knew that. But plus, I'm not changing, I'm just making it bigger and clearer. Sorry. Sorry. Maxwell says if you have magnetic field up here at the top of the circuit, it's from any combination of two possible contributions. One, the standard current, the standard flow of charge that's going through dq dt, like this all assumes, remember, and you know this from lab and from current is dq dt. It is number of charges rushing by a certain point in space per certain unit of time. That's what current is, charges rushing by in time, right? So Maxwell says if you've got a magnetic field around this loop, one possible reason is that regular charges are flying through the area bound by the loop. But the other possible reason, the other contributing factor to magnetic field could be electric flux, electric field, well, yeah, electric flux flying through the area bound by the loop. Where did I get where did I get epsilon naught ddt, double integral E dot ds? I literally just, I'll write it. I'll just write it. Where did I get that from? I'm looking at the time. Where did I get this from? Where I got that seemingly complicated thing from? I'm saying current is dq dt. And Q, if you rearrange Gauss's law, Q is flux times epsilon naught, right? Flux is Q over epsilon naught. So in other words, this is just saying in English, you might not have charges passing through an area, but you might have field lines fluxing through that area. Add up all the electric field lines and the actual charges going through an area, and then you'll have the total reason for magnetic field. Space knows to have magnetic field here if there's either flying charges or not flying, flowing charges or flowing electric field lines. Because for every charge, there is an electric field line, right? So Maxwell corrects Ampere's law. And by doing this with this extra term called the displacement current, by doing this, the four equations together, this correction now makes this law look like one of the other laws you'll see in a second. And it makes the whole package of these four equations so unified that the whole package of four equations become now known as Maxwell's equation. Once he just corrected one term on one of them, they all become Maxwell's equations. So I'm going to rewrite them for you right now. And we're almost done. We have 11 minutes. We're almost at the punchline of this, but I'm going to rewrite them for you. So I'm saying Maxwell deeply considers Ampere's law, says it's incomplete. It needs another term to actually satisfy all situations. Here's the other term. And to write the other term, he just uses the definition of current and Gauss's law, just rearranges. So he adds the other term. Now, the other term says, if you look at it, it says, in effect, if you change the electrostatic flux through an open area, if you start pumping electric field lines through an open area, you'll get a magnetic field in the closed path bounding that area, right? The logic of it again is, look, pumping electric field through an area is just like sending charges through it. If sending charges through an area, i.e. sending a current through an area, is what made magnetic field in the first place. So what Maxwell is saying is, if sending charges through an area makes magnetic field, then sending new electric field lines through an area, same effect on space. Field lines are the information of charges. So if you send charge information through an open area, if you change the rate at which electricity is fluxing through an area, you'll get magnetism in the closed path bounding that area. So that may sound familiar. That means this extra term that Maxwell just added to Ampere's law looks very much like the opposite of the term in Faraday's law, right? So if we now put the four laws together and we apply them to empty space, to free space, what do I mean by free space? I mean a point in space where there's no charge at all and no current. So I mean a point in space where rho equals, whoops, sorry, equals I, which equals zero. A point, so I'm going to, anywhere I see, I'm not rho, I'm not rho, I mean Q, sorry. Anywhere I see a Q in those equations, I'm going to cross it out to zero. Anywhere I see an I, I'm going to cross, I'm just looking at a random point in space that has nothing in it, that's just empty. Then the equations become, okay, this is just any random point in space that has nothing in it, free space. These four equations apply. These are Maxwell's equations. Now look carefully. I know we have 7 minutes. We're just about there. But and I know this can be intimidating or a lot, but just look carefully. Look at the equations. They're a very tidy package now. Like again, the left side, two statements about electric field, two statements about magnetic field, two statements about closed surfaces, two statements about closed paths. That's the left side. The right side, okay, two of them go to zero. Again, we're looking at a point in empty space where there's no charge and no current. And two of them, the other ones, are exactly the same as each other, mirror images, only one has a negative sign. In other words, if you stare at these, it says anywhere in space, if you consider any open area in space and you change the magnetic field, you change the magnetic flux through an open area in space, you'll get electricity in the perimeter of that space. But if you look at any space, any area in space, and you change the electricity, the electric flux through it in time, you'll get magnetism in the perimeter of that space. That's what these laws say. So what does that mean in English? And more to the point, what Maxwell said to himself is he's like, whoa. He's like, Maxwell noticed that. He's like, wait, E comes from a change in B, and B comes from a change in E in the exact same way, but one with a negative sign and one not. Like, what does this mean? He asked himself, is there any way I can break apart these equations and just get equations, an E equation just with E in it, and a B equation just with B in it, so I could see what's going on? Why are they related to each other this way? Now, he had multivariable calculus to do that. He applied these things called Stokes' theorem and Curl's theorem, and he was able to decouple the two equations to get a E by itself and a B by itself. And what he got was this. Well, I'll just leave it at that. And same thing for the B. We got a second order partial differential equation for E and the same one for B. We've got 4 minutes. When he took those two integral equations and decoupled them to get E by itself and B by itself, he got something that looks very intimidating at first. It says the second time derivative of E equals a constant times the second space derivative of E. And same thing for B. That looks really intimidating. It's a second order partial differential equation. But here's the thing. You've all seen this second order partial differential before in this course. You've seen things of this form. You've seen something that looks exactly like it. You've seen it with Y's, but this is with field. You've seen it with vertical position. This is with fields, but it's the same form. Second time derivative equals a constant times second space derivative of the function. I don't know if you recognize it or not, but this equation that he found, the equation that the E field follows in free space and the equation that the B field follows in free space is the wave equation. And in the wave equation, the square root of whatever that constant is the speed at which the wave travels. So what does this mean with 2 minutes left? This means, say you create a current that is like a cosine function of time, right? A current that's a cosine function of time. Cosine, you can take derivatives forever and they never stop, right? So imagine you make a current that's a cosine function of time. So the current's going like this. It creates a magnetic field going like that. But the magnetic field has a derivative. It's changing in time. So it goes through an area, it makes an electric field in the perimeter of the area that it's going through because it's changing in time, because cosine, you can take a derivative of cosine, right? So the magnetic field makes an electric field that goes around the perimeter of its area. But the electric field, you can take a derivative, so it's changing in time. So then it makes a magnetic field around the perimeter of the area that it's going through. And this goes on and on and on. We have 2 minutes left, right? I'm saying literally, if you make a current that's a cosine function of time, the current will make field through that area. That field will make field through that area, will make field. But so each field will be at right angles to the last one. E will make B, B will make E. They'll each be at right angles, but one of them has a negative sign and one of them doesn't. So when you go from the B field to the E field, you'll make a right-hand rule turn. But then when you go from the B field to the E field, there's a negative sign. So you make a left turn and then a right turn and then a left turn. So you don't circle back in on yourselves. The fields make fields and make fields and make fields and blast away from the thing that created them. They blast away in the manner of a wave. The fields propagate as a wave at the speed of as the speed of square root of 1 over epsilon naught mu naught. You could check on your calculator. The square root of 1 over epsilon naught mu naught is the speed of light. So what happens is light is the perpetual self-mutual induction of E and B fields flying away from the thing that caused them. I know it's 1:30, I'm just about done. But the point of this is this. What light is waves through the electromagnetic fields. The light is the updating of whenever something changes in the field over here and space has to find out over here, the update in the field ripples through the field in a manner of waves. But remember, waves were unthingy pulses that we believed in because they were propagating through thingy media. You believe in water waves because there's a bunch of water molecules wiggling back and forth. Here, light is a wiggle through a medium. What's the medium? The medium is fields. What are fields? Fields are just vectors of information. The vectors are wiggling back and forth. The field lines are wiggling back and forth. So what light is an unthingy vibration through an unthingy medium. Light is an immaterial pulse propagating through an immaterial medium. It is raw information. The speed of light is the rate at which the universe updates itself. That's it. You've been a great class. I really appreciate working with you. I'll talk to you over time. Have a great week and good luck on your final.
Thank you, Professor.
Thank you. Thank you.